Hello everyone. I've been meaning to do a video series on learning assembly language on Atari 8-bit computers. It's sort of like a nostalgia that I've never known. I've never programmed assembly on an 8-bit computer, and I've never had an Atari or anything. So this is kind of like I'm trying to have the nostalgia of it, you know? It seems kind of cozy, and for some reason, maybe it's because it was like a simpler time and more optimistic. But let's see. And if you want to learn it, then what we're going to be using are three basic things. I don't know it, so if you watch this with me and you do the same thing, then you'll learn it also. That's basically the idea. I like to use the documentation that anyone can get online. So all of these links are going to be in the description. We're going to be using this book, Atari Roots, and we're going to be using an emulator called Altira, and we're going to be using the assembler actually in the Atari 8. I think we're choosing an Atari 800 XL. And what that means, like you could like you can use like Visual Studio. I read a little bit about this and program on it with the nice modern IDE, and then you click a button, run, and it launches it in the emulator and all that. But I want to feel like what was it like to program on the actual 8-bit computer. So that's what we're going to try to do. I have no idea what you can actually do. Like I'm a functional language programmer mostly, so it's like this is the exact opposite. I don't really envy, like I don't really have too much excitement about making a game in assembly, but I want to know what it's like. So it's a little bit of an exploration for me. All right, so I think this first video is just going to be kind of orientation and reading the intro for the book. I like to read it all out loud, so if you are like, hey, I just want to get there and learn stuff, this series probably isn't for you. You know, we want to feel cozy and all that while we're learning the stuff too and not feel rushed. So there's that. Okay, let's get started here. What do I want to say? All right, so the emulator, I looked around and it looks like Altira is the best one. It's available on Windows, and I think you can run it on Linux also if you use Wine or something like that. I'm going to be using Windows for this, and I'll be sharing my screen like this so you can follow along. I don't know if it's like too hard to read because usually I don't share like a whole desktop, but I think because I will be using an emulator, it might be easier to do it this way. So Altira, if you read this whole page, the guy never talks about, like, says who he is, I don't think. But I had to look around, and his name's Avery Lee, and looks like he was really into 8-bit computers and decided to make a emulator. And that's what we can benefit from. I'll show you how I download it and everything like that. So you just have to do that also. I think we go down, scroll down on this page, and we see some binaries here. I am not using an ARM computer, so I just download it here. Should be in my download folder, and I am going to put it inside my Atari folder here. I will unpack this, extract all. Here we go. Okay, perfect. Now I can get rid of this one. And in here, I think we need the actual ROM because otherwise it doesn't really do anything. So, how do I find the ROM? I think they tell you that over here. Before you begin, first you'll need some software to run, and you'll need some kernel ROMs. Altera has an internal kernel that can be used to run Atari software, without needing any Atari ROM images. However, the kernel is re-implemented from scratch. So let's try to get the real one. So we'll type, I think I did a search like this before. It was like Atari 800 XL ROMs, I think I typed. And then I saw this, Best Simple ROM Pack, and I think I clicked on, I think it was this one I clicked on. And then there was a post that actually just had it included in here. Here it is. Atari OS ROMs. And then if you download that, you will get that file. Right? Okay. And then I put that file in here and unzipped it over here. So ROMs, Atari OS ROMs, and you can look under XLXE, and I'm using the Rev 2. I'm not sure why I chose Rev 2 at all. Oh, because it's the XL and not the 800XE. Right, so I put this ROM, just copy this one, and we're going to put it in the Altera folder so that it's easy just to search. Now I'm going to run the 64-bit version. At your own risk, run anyway. Alright, cool. So we have an Atari sort of running, but I think we're going to configure the system now, and under 800XL CPU firmware. So it looks like it found it. Maybe this is because I installed it before, but what you do is you do scan, and then you give it like the directory that you're in, and then it said it found one, and then you would go under the XLXE, and then you can see like this was the Altera stuff, but then it found this one here, so it loaded it. You just click like, add, and then it will show up, and then you select it over here as the operating system you want to use. I didn't add a basic, so this is just a basic that they have. I don't think there's anything else to really change here, so let's not worry about that. All right, cool. So we have something here, and we're going to be using the Max 65 assembler, but we're not there yet. We're going to be learning about assembly from this book, Atari Roots, and you can kind of just like follow along and click. I'll try to name the videos like Chapter 1, Chapter 2, and probably we won't cover full chapters in a video. So I'll probably, do Chapter 1, Part 1, Chapter 1, Part 2, etc. To see how that goes. I don't think we're actually like typing much until I don't know how many chapters in. Probably chapter 4. So if you're really like, I just want to see, then you can jump ahead. Also, I think I'm going to be reading the book from a scan of the book rather than the website, because it just feels a little bit more real to me. So let's do that. So Atari Roots, a guide to Atari assembly language, and here's the Atari 800 or some kind of XL system, I think. And it has like, how do I zoom out? It has the brain attached with branches. That's pretty cool. Learn how to program 6502 assembly language the easy way. Atari Roots. Yep. Data most. All right. Thank you, Maureen. Table of contents, we're going to learn a little bit about what assembly language is, bits, bytes, and binary, what the 650 CPU is, writing assembly programs, running it, about addresses, looping, calling assembly programs from basic, programming bit by bit, okay, assembly math, beyond page 6, what I guess there's like memory pages or something. IO and U, Atari graphics, and advanced Atari graphics. Cool. All right, if this gets a little tedious, then I'm gonna just like kind of skip over some of it. Preface. Um, Maybe make this a little bit bigger. Many books have been written about the 6502 assembly language, but this book is different in several important ways. Until now, there have been two main kinds of books about 6502 assembly language. There are generic books that make no mention of Atari computers, and there are reference books that are full of information about Atari computers, but they are so technical that only experts can understand them. But there was a distinct shortage of books designed to teach Atari users who knew a little basic how to start programming an assembly language. This is what I noticed when I started like, okay, how do I learn this stuff? And it was like, oh, learn 6502, but it doesn't say like at all how to, like I don't know how an Atari works at all. So I just wouldn't know how to go from something that, the 6502 was used in Apple IIs or 2Es, I don't know. And it was used in Commodores, it was used in Ataris. Like, uh, it's not the same thing in all of those systems. Like, you can't write exactly the same way. So, well, anyway, this book was written to fill that void. It's written in English, not computerese. It's written for Atari users, not professional programmers, though they might find it useful. Every major topic it covers is illustrated with at least one and often more simple, informative, useful programs. This book is also unique in several other ways. It's the first assembly language guidebook that has been user tested on Atari's new XL series computers, and every program in it will work on Atari's older computers too. It's the first book to cover the operation of OSS Max 65 assembler, one of the most popular Atari assemblers on the market, as well as the operation of Atari Assembler Editor cartridge. I think those are the two big Atari assemblers that were available on Atari. No matter what kind of computer or assembler you own, the book you are now reading is probably the easiest to understand assembly language textbook you'll ever own. In this book, you'll find for the first time between book covers everything you'll need to know to start programming in Atari assembly language and to start running your programs on an Atari computer system. I like how it's like talking about like everything being new and stuff like that. Best of all, this book will have you writing assembly language programs before you know it. And by the time you finish, you'll be well on your way to becoming an expert assembly language programmer. All you'll need is this book, an Atari computer or emulator, and a few other supplies. They are a machine language assembler and debugger. This is the Max 65 from Optimized Systems Software of San Jose, California, just in case there's optimized system softwares in many other cities, or the Atari Assembler Editor cartridge. If you own other kind of assembler, you can probably use it without too much difficulty. Okay, it doesn't matter too much here. You'll need the Atari Basic cartridge, which I think it comes built into the emulator. Floppy drive, yep, it's in the emulator. And a line printer. God, I hope not. As you learn more about assembly language, you may also want to buy more books about Atari. Alright, cool. Introduction. So now we are in the introduction area here. If your Atari doesn't understand you, it's maybe because, let me make this, don't speak its language. Together, we're going to break that language barrier. This book will teach you how to write programs in assembly language, the fastest running, most memory efficient of all programming languages. This book will also give you a good working knowledge of machine language, your computer's native tongue. It will enable you to create programs that would be impossible to write in BASIC or other less advanced languages. They make it sound like assembly is the most advanced, but in fact, it's like the most primitive, right? Anyway, and it will prove to you that programming in assembly language is not nearly as difficult as you may have thought it would be. All right, so let's kind of gloss over some of this. Write programs that will run 10 to 1,000 times faster than programs written in BASIC. I don't, yeah. Use up to 128 colors on your video screen simultaneously. You know, like, can you imagine, like, CSS is such a pain. Like, this feels kind of easier, right? You only have 128 colors, so it's a little bit easier. Custom design your own screen displays, mixing text and graphics in any way you like. You'll also be able to create your own customized character sets. I think they made a lot of games like by just like taking characters and changing the way characters look so that they look like, you know, a graphic or several characters together, and that's how sometimes they did graphics. Design animated screen display using both player missile graphics. I don't really know what that term means, and character animation techniques. Use both fine and coarse horizontal and vertical scrolling in your programs. I don't know what fine and coarse scrolling means. Um, you'll even learn how to create sound effects that are too complex to be programmed in BASIC. Well, I don't even know how to do it in BASIC. Use graphic modes that BASIC doesn't support. Write programs that will boot from a disk and run automatically when you turn your computer on. In other words, once you learn how to program in assembly language, you'll be able to start writing programs using the same kind of techniques that professional Atari programmers use. Many of those techniques, oops, you don't see that, but my monitor wanted to shut off. Many of those techniques are downright impossible without a knowledge of assembly language. Finally, and even more important, as you learn assembly language, you'll also be learning what makes computers tick. That's pretty cool, right? And that will make you a better programmer in any language. Assembly language demystified. This book has been carefully tailored to take the drudgery out of learning assembly language. It's packed with simple programs, sample programs, and routines. Chapter 1 will introduce you to assembly language and explain the differences between assembly language and other programming languages. Chapter 2, you'll learn about bits, bytes, and binary numbers, the building blocks that program designers use to create assembly language programs. You'll even find some easy to use basic programs that will automatically perform hexadecimal and binary conversions and will help take the mystery out of hex and binary numbers. In Chapter 3, we'll start probing the mysteries of the 6502 microprocessor chip, the heart, or perhaps more accurately, the brain of your Atari computer. In Chapter 4, you'll start writing assembly language programs. Alright, so we have to hang in there until Chapter 4. And by the time you finish the book, you'll be well on your way to becoming an accomplished assembly language programmer. Alright, we got to get to Chapter 4, right? Chapter 1, Introducing Assembly Language. Start programming immediately in machine language. Turn on your Atari computer and type in this program. Then run it, type a few words, and you'll see something very interesting on your screen. Alright, let's do that. Here we go. Does it make it bigger if I do this? Yeah, it does. Well, except I can't see the code here. We'll do something like this. Oops. Does that look good? I think that works. Alright, so all the REM are just like comments, so we don't need that. I think I'm in basic, so I can type 60 graphics 0 print. I think there's like little sounds on here too, isn't there? But I'm not capturing that. Let me do that here. 1 second. La 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 la. All right, let's see. You hear that? I think so. Poke 755, comma 4, 110, open, number 140 K colon 120 get number 1 K 130 print whatever this is K. It's kind of funny how some of them, like this one has a semicolon at the end and the others don't. Go to 120. Alright, so I'm going to type run now. It says then run it. Type a few words. Okay. I type a few words. It looks like everything's upside down. Line 60 clears your computer screen with graphics 0. Line 110 opens the Atari keyboard as an input device. Then in 120 to 140, there's a loop that prints typed in characters on your screen. But the most important line in this program, the line that makes it do what it's supposed to do, is line 100. The active ingredient of line 100, the instruction poke 755, 4, is actually a machine language instruction. In fact, all poke commands in BASIC are machine language instructions. When you use a poke command in BASIC, what you're actually doing is storing a number in a specific memory location in your computer. And when you store a number in a specific memory location in your computer, what you're doing is using machine language. Alright, well cool, we used machine language, guys. We did it. But I don't think we're experienced assembly programmers just yet. Under the hood of your Atari, every computer has three main parts: a central processing unit, CPU, memory, usually divided into two blocks called random access memory, RAM, and read-only memory, ROM, and input-output I/O devices. So here's the data bus, I/O, CPU, RAM, ROM, and address bus. Okay. Your Atari's main input device is its keyboard. Its main output device is its video monitor. Other I/O devices that an Atari computer can be connected to include telephone modems. Yeah, those existed. Maybe they still do. See my little... Oh, maybe you can't see. It's my little kitty cup. Graphics tablets, cassette data recorders, and disk drives. In a microcomputer, all of the functions of a central processing unit are contained in a microprocessor unit, or MPU. Your Atari computer's MPU, as well as its CPU, is a circuit using large-scale integration called a 6502 microprocessor. The 6502 microprocessor, your computer's command center, was developed by Mo's Technology Inc. Several companies are now licensed to manufacture 6502 chips, and a number of computer manufacturers use the 6502 processor in their machines. The 6502 chip and several updated models, such as the 6502A and the 6510, are used not only in Atari computers, but also in personal computers manufactured by Apple, Commodore, and Ohio Scientific. That means, of course, that 6502 assembly language can also be used to program many different personal computers, including the Apple II, II Plus, IIe, and Apple III. I didn't even know there was an Apple III. All Ohio Scientific computers, the Commodore PET computer, and the Commodore 64. And that's not all. The principles used in Atari assembly language programming are universal. They're the same principles that assembly language programmers use no matter what kind of computer they're writing programs for. Once you learn 6502 assembly language, it will be easy to learn to program other kinds of chips, such as the Z80 chip used in Radio Shack and CPM based computers, and even the powerful newer chips that are used in 16-bit microcomputers such as the IBM PC. Wow, it's like looking through the past, into the past. The fountains of ROM. Your computer has two kinds of memory: random access memory, RAM, and read-only memory, ROM. ROM is your Atari's long-term memory. It was installed in your computer at the factory, and it's as permanent as your keyboard. My keyboards don't last very long. Your computer's ROM is permanently etched into a certain group of chips so it never gets erased, even when the power is turned off. For most home computer owners, that's a good thing. Without its ROM, your Atari wouldn't be an Atari. In fact, it wouldn't be much more than an expensive high-tech doorstop. The biggest block of memory in ROM is the block that holds your computer's operating system, or OS. Your Atari's operating system is what enables it to do all those wonderful things that Ataris are supposed to do, such as accepting input from the keyboard, displaying characters on the screen, and so on. ROM is also what enables your computer to communicate with peripherals such as disk drives, cassette recorders, and telephone modems. If you own one of Atari's XL series of computers, your unit's ROM package also contains a number of added features such as a built-in self-diagnostic system, a built-in foreign language character set, and built-in BASIC. RAM is fleeting. ROM, as you can imagine, was not built in a day. Your Atari ROM package is the result of a lot of work by a lot of assembly language programmers. RAM, on the other hand, can be written by anyone, even you. They don't think much of us just yet. RAM is your computer's main memory. It has a lot more memory cells than ROM does, but RAM, unlike ROM, is fleeting. The trouble with RAM is that it's erasable, or as a computer engineer might put it, volatile. While you turn your computer on, the block of memory inside it that's reserved for RAM is as empty as a blank sheet of paper. And when you turn your computer off, anything you may have in RAM disappears. That's why most computer programs have to be loaded into RAM from mass storage devices such as cassette data recorders and disk drives. So we still use disk drives, right? But they're kind of like SSDs now. SSDs. After you've written a program, you have to store it somewhere so it won't be erased when the power goes off and erases your RAM. Your computer's RAM, or main memory, can be visualized as a huge grid made up of thousands of compartments or cells, something like tiers upon tiers of post office boxes along a wall. Each cell in this vast memory matrix is called a memory location, and each memory location, like each box in a post office, has an individual and unique memory address. The analogy between computers and post office boxes doesn't end there. A computer program, like an expert postal worker putting mail in post office boxes, can get to any location in its memory about as quickly as it can get to any other. In other words, it can access any location in its memory at random. And that's why user addressable memory in a computer is known as a random access memory. Its letters are numbers. Our post office analogy isn't absolutely perfect, however. A post office can be stuffed full of letters. A post office box can be stuffed full of letters, but each memory location in a computer's memory can hold only one number, and that number can represent only one of three things: the stored number itself, the code representing a typed character, or a machine language instruction. So it's kind of interesting. So the number is just like, yeah, you're putting a number in there, so it's just a number. 2 is like a typed character because we're dealing with an 8-bit computer, and the character set ASCII is an 8-bit system. So, it can be a character, and or it can be a machine language instruction. And that's why we're learning this. What next? When a computer goes to a memory location and finds a number, it must be told what to do with the number it finds. If the number equates to just a number, then the computer must be told why the number is there. If the number is a code representing a typed character, then the computer must be told how the character is to be used. And if the number is to be interpreted as a machine language instruction, the computer must be told that too. The instructions that computers are given so that they can find and interpret the numbers stored in their memories are called computer programs. People who write computer programs are of course called programmers. The languages that programs are written in are called programming languages. Of all the programming languages, assembly language is the most comprehensive. Well, yeah, in a way it has to be because it's basically the machine's language, and if there was another language that was higher level that couldn't turn into assembly language, then it means that it couldn't actually run on the computer. Running a machine language program. When your computer runs a program, the first thing it has to be told is where the program has been stored in its memory. It's kind of a funny thing, right? It's like the computer starts up, it's like, where's that program? I don't know where it is. It's like as if you have a memory of something, but you can't. I guess it's like a dream when you wake up. Sometimes you ever sit there and you're like, oh, I almost have it, but I can't remember it. And then you remember it, it's like it all comes back at once. What am I talking about? Once it has that information, it can go to the memory address where the program begins and take a look at what's there. If the computer finds an instruction that it's programmed to understand, then it will carry out that instruction. The computer will then move on to the next address in memory. After it follows the instruction it finds there, it will move on to the next, and so on. The computer will repeat this process of carrying out an instruction and moving on to the next one until it reaches the end of whatever program has been stored in its memory. Then, unless it encounters an instruction to return to an address within the program or to jump to a new address, it will simply sit there, patiently waiting to receive another instruction. As you know, programs can be written in dozens of computer languages such as BASIC, COBOL, Pascal, Logo, and so on. Out of these, we're still using COBOL. In fact, I want to do a series on COBOL. I want to learn it. Languages like these are called high-level languages, not because they're particularly esoteric or profound, but because they're written at too high a level for a computer to understand. A computer can actually understand only one language, machine language, which is written entirely in numbers. So, before a computer can run a program written in a high-level language, the program must somehow be translated into machine language. Programs written in high-level languages are usually translated into machine language using software packages called interpreters and compilers. An interpreter is a piece of software that can convert a program into machine language as it's being written. Sort of. Your Atari Basic Interpreter is a high-level language interpreter. Interpreters can also be used to convert a few other high-level languages, such as Logo and Pilot, into machine language. So, like, Python is still interpreted, right? A compiler is a software package designed to convert high-level languages into machine language after they are written. COBOL, Pascal, and most other high-level languages are usually translated into machine language with the help of compilers. Yeah, so that's like C and Rust and Zig and all those cool languages. Machine language assemblers. Interpreters and compilers are not used in writing assembly language programs. Assembly language programs are almost always written with the aid of software packages called assemblers. A number of other assemblers for Atari computers are available, including Atari's very advanced macro assembler and text editor package. An assembler doesn't work like an interpreter or like a compiler. That's because assembly language is not a high-level language. One could say, in fact, that assembly language is not really a programming language at all. Actually, assembly language is nothing more than a notation system used for writing machine language programs using alphabetical symbols that human programmers can understand. What we're trying to get across here is the fact that assembly language is totally different from every other programming language. When a high-level language is translated into machine language by an interpreter or a compiler, one instruction in the original programming language can easily equate to dozens, sometimes even hundreds of machine language instructions. However, oops, when you write a program in assembly language, however, every assembly language instruction that you use equates to just one machine language instruction with exactly the same meaning. In other words, there is an exact one-to-one relationship between assembly language instructions and machine language instructions. Because this one-to-one correspondence, machine language assemblers have a much easier job than interpreters and compilers have. Usually I stop if I read something that, like, in my other videos about, like, doesn't make, if it's hard to understand or not clear. But so far I feel like everything they said is, like, really clear. But, we're not coding yet. Since assembly language programs, often called source code, can be converted directly into machine language programs, often known as object code, an assembler can just zip right along, turning source code listings into object code without having to struggle through any of the tortuous translation contortions that interpreters have to face each time they carry out their appointed rounds. It's getting very metaphorical. Assemblers also have one other advantage over compilers. The programs that they produce tend to be more straightforward and less repetitious. Assembled programs are more memory efficient and run faster than interpreted and compiled programs. Well, I guess it depends on the programmer, right? The programmer's plight. Unfortunately, a price has to be paid for all this efficiency and speed. And the individual who pays for that price is, sadly enough, the assembly language programmer. Ironically, even though assembly language programs run much faster than programs written in high-level languages, they require many more instructions and take much longer to write. One widely quoted estimate is that it takes an expert programmer about 10 times as long to write an assembly language program than it would take him or her to write the same program in a high-level language such as BASIC, COBOL, or Pascal. On the other hand, assembly language programs run 10 to 1,000 times faster. How it works. Oh dear, like how much longer do we got here? Alright, we're almost there, and then I'll stop at the end of the chapter. Machine language, like every other computer language, is made up of instructions. As we have pointed out, however, every instruction used in machine language is a number. The numbers that computers understand are not the kind that we're accustomed to using. Computers think in binary numbers, numbers that are nothing but strings of zeros, ones and zeros. Here, for example, is a part of an actual computer program written in binary numbers. Okay, 000110000. It doesn't take much imagination to see that you'd be in for quite a struggle if you had to write long programs, which typically contain thousands of instructions in binary style machine language. With an assembler, however, the job of writing a machine language program is considerably easier. Here, for example, is the above program as it would appear if you wrote it in assembly language. CLC, CLD, LDA, O2, ADC, O2, STA, CB, RTS. So I guess like the fourth, 1, 2, 3, 4, 5, 6, fourth and 6 are the same. 1, 2, 3, 4, 5, 6. Yeah, these are both binary for the number 2. And it says 2 here, so I guess this is how you say 2 in binary. You may not understand all of that yet, but you'll have to admit that it at least looks more comprehensible. What this program does, by the way, is add 2 and 2, and then it stores the results of its calculation in a certain memory location in your computer, specifically memory address 203. I wonder how it knows 203. Is that this? Anyway, who cares? Later on, we'll come back to this program and take a closer look at it. Then you'll get a chance to see exactly how it works. First, though, we're going to go into a little more detail about assemblers and assembler language. Assembly language is written using three-letter instructions called mnemonics. Some mnemonics are quite similar to basic instructions. One assembly language instruction that's much like a basic instruction is RTS. The last instruction in sample routine we just looked at, RTS, written as this in machine language, means return from subroutine. So return from subroutine. It's used much like a return instruction in BASIC. There's also assembly language mnemonic that's similar to BASIC's go sub instruction. It's written JSR, which means jump to subroutine. And then we get its binary. Not all assembly language instructions bear such a close resemblance to basic instructions, however. An assembly language instruction never tells a computer to do something as complex as draw a line or print a letter on the screen, for example. Instead, most assembly mnemonics instruct computers to carry out very elementary tasks such as adding two numbers, comparing two pieces of data, or as we've seen, jumping to a subroutine. That's why it often takes vast numbers of assembly language instructions to equal just one or two words in a high-level language. Source code and object code. When you write an assembly language program, the listing that you produce is called source code. I think we read this already. Since it's the source from which a machine language program will be produced. Once you've written an assembly language program in source code, you can run it through an assembler. The assembler will then convert it into object code, which is just another name for a machine language program produced by an assembler. The speed and efficiency of machine language. Since assembly language instructions are so specific, you might even say primitive, it obviously takes a lot of them to make up a complete program. Many more instructions than it would take to write the same program in a high-level language. Ironically, machine language programs still take up less memory space than programs written in high-level languages do. That's because when a program written in a high-level language is interpreted or compiled into machine language, big blocks of machine code must be repeated every time they are used. But in a well-written assembly language program, a routine that's used over and over can be written just once and then addressed as many times as needed with JSR, RTS, jump subroutine, and return subroutine, and similar commands. Many other kinds of techniques can also be used to conserve memory in assembly language programs. Alright, we're gonna stop here. Then we have two more chapters, and then we can start coding assembly. So there we go. I know it's probably a little bit long. I hope it can be a little enjoyable. I just kind of just like get into it and like try to enjoy the moment. Anyway, if you enjoyed that, please do like and subscribe. I have a Discord that you can join too. There's really no questions that I can imagine coming up just yet, but if you do, you can bring that up there and I'll be happy to answer. And otherwise, I don't think I'll be doing like I was working on Nicks before and I was doing those very regularly, but I don't think this is something I'm going to do like every day or anything, so I'm not sure like what the frequency will be. But we'll get to it. We'll get chapter 2 and I'll put this all in a playlist so that once we have a few of these, they can all be kind of grouped together. All right, I hope you're all doing well and talk to you soon. Bye bye.